speaker is Alexander.
Riccardo.
Riccardo,
yeah.
which is dressed like Alexander today.
Yes. So my colleague Riccardo is sick, unfortunately, but I have the honor to present his findings, his work. Riccardo works on the flapping setup for the wind tunnel. So this year we did an extensive experimental campaign in the wind tunnel. What you see here is the wind tunnel. Wind is coming out of the screen. We have a wing. In the setup we have high-speed cameras, a bubble generator and a laser to do aerodynamic measurements. Luc will go into that direction in his talk. We have a flapping setup which is here under the table. That's the main focus of this talk, the flapping setup of Riccardo. And we have a motion capture system which can track the deformation of the wing, the motion of the wing, which I'll tell about in my own presentation. Basically, the flapping setup of Riccardo aims to make it possible to flap in any way with a Robird wing. It has two axes of motion. It has a plunging motion and it has a pitching motion. And basically, with the electronics and the software, you can input any feasible motion within the constraints, within the limits of the motor torques. It works by two motors with cable drives. It has a 6 Dov force torque puck, so that we can also measure all the forces and the torques which are exerted on the wing. It has encoders on both axes, so that you can see all the motion. And it has extensive electronics and software which was redesigned multiple times due to problems with the
electromagnetic compatibility.
Yes, electromagnetic interference was a big problem, but that all works. But basically these motors use, I think, 30 amperes, 30 amps, and when they spike they give noise throughout the entire system. So the electronics needed a lot of shielding to get rid of that. And what we've done is we've flapped with various wings, with various parameters in the wind tunnel, recording this type of data. The top graph is the forces from the force puck. The bottom graph is the encoder data. So you see that we flap with a big flapping motion and a smaller pitching motion, in this case with a 90 degrees phase shift between both, which is the standard way in which the Robird should be flapping. And we've recorded the forces. And if you, Riccardo has averaged all this over various periods to get the lift force, the thrust force, the used mechanical power, and the actual force on the force puck, so on the root of the wing. And basically what you can see, the various colors are, the turquoise, I think it's called, is 0 meters per second. Then we have about 8 meters per second, 10.5 and 15.8 meters per second, which corresponds to Struwelon numbers of 0.2, 0.3, 0.4 and infinite, let's say. For the ones who don't know what the Struwelon number is, basically it relates the frequency at which you flap with the flow, the incoming flow. So it says something about how quickly you flap with respect to the flow that is passing by the wing.
And it is known that all animals that actually move in that way, more or less, fishes and birds, stay within a certain range of that.
Yeah, within 0.1 to 0.5, if I'm correct.
0.5 is a bit high.
0.5 is a bit high, exactly. So we measured from basically between 0.2, 0.3, 0.4, that was our main measurement range. And what you can see is that the lift stays approximately, so what we varied per experiment, we varied the phase shift between the pitching and the plunging. That's expected to give a lot of influence on the thrust and the lift, which we based on the models from Professor Wiemaker. And what you see is that the lift stays approximately constant while sweeping phase between both, whereas the thrust has a strong optimum around minus 60 degrees phase shift, which also corresponds to the modeling.
But it seems that, the question is, I asked what God simply remember the discussion and said, I would like to have a line, which is, puts in the line where now the bird is flapping, because now you see that the maximum is kind of shifting, so you could actually adapt the phase shift to get a better thrust.
I'm not sure if I understand, but we also have that data, I think, but this is just the...
No, what I said, because the discussion I had with Luc and Riccardo, the bird has now a fixed phase shift, which is a vertical line on this graph.
Yes.
Okay, so then you see that whatever speed you go, it's always the same. So in certain speed, it's not the maximum efficient, maximum thrust, because the maximum shifts a little bit.
Yeah.
Okay, so if you could do a mechanism that you could change that, you would go faster, basically.
Yeah, so you could adapt your phase shift during flapping to have either maximum peak thrust, maximum efficiency. That's the choice you can make. Yeah.
Do you want to change it within one cycle, Stefano?
No, but it's suppose that it's just an observation that, you know, if you would have different speeds, you would have different relation between the...
Yeah.
You have to adapt your phase shift with the operation that you are
operation that, yes.
Yeah.
What we've tried is disconnect the rear shift and then see what it does when it flies.
In a natural way.
Yeah, then it does it in a natural way. There were many forces on the front connector.
Because you need to find elasticity. Is an energy through, is an impedance matching issue. You want that the maximum power that gets from the actuations is good in thrust. It's really an impedance matching. That's why, you know, if you do this is something I mentioned before. If you would be able to understand this in this context, you know, generalize what is known in communication lines in electrical magnetic fields, you would have basically an impedance matching between a fluid and a solid, that you would have a maximum thrust. And if you can model that, for example, by doing the numeric and solve it, that would be something pretty good.
Maybe you want to fly at minimum required power.
Yes, that's what. Exactly. But you want at least that the power you use is maximally used. Efficiency is always the good thing you want to have, right? You don't want to waste energy anyhow, and that's what animals do all the time. Yeah.
And that's an interesting remark, minimum power, because what we see now is that minimum power input by the motor is approximately at the same spot as where the efficiency is, whereas aerodynamically you would not expect that, but most of our power now goes into the inertia of the wing. So really moving the wing takes most of the power at the moment. And at some point for the highest flow velocities, the motors ran into their limits, so you can see that it simply could not cope, it did not have the force to make the movement.
Alex, can you define the direction of these forces?
Yeah, so the lift force is, if you have the wing, the lift force is, okay, so there's a bit more to it. So we did the experiment with left wings. Basically the lift force is the force that points upwards to the normal of the Robird, or no, that's normal to the incoming flow. The drag force / thrust force is parallel to the incoming flow. And the actual force is actual to the Robird, but the wing is moving. So there's a wing frame, there's a world frame. So the forces defined there are really in the with respect to the incoming flow of the wind tunnel. Yeah.
So when you say thrust force, it's actually mixed between drag and
So
it's a mix between a drag and pushing forward of the wing. Right?
It's a mix of everything, because
it's not only thrust as it would be in an airplane, given by the engines. There is also the drag.
Well, it's not that simple, because we have a moving wing. But overall, it's basically the forces are defined in terms of the direction of the incoming flow, right? So, and the wing motion gives rise to those forces in combination with the air.
And the fact that it's negative, it means it pushes the bird.
So the fact that it's negative means that the bird would go backwards. Yes.
Yeah.
Yes.
And I think, you know, this what you just said is, I think, is very often is very unclear and sometimes wrongly, in my opinion, defined. Because of course, for an airplane, it's very clear because nothing moves, and you want to move in a certain direction. It's very simple. Gravity is always in a certain direction, and you want to prevent it falling. That's what I should call lift, right? What is opposite to that? And you move as a rigid body in a certain tangential motions. That should be the direction that defines thrust, and the rest is. And this, if you define it like this, of course, it's independent of what kind of thrust you use, whether you flap or you use any kind of motion. That is what you would have, right? Because eventually it's about something that moves in the fluids and prevents the fall.
Because the Robird is under an angle of attack. The wing is constantly changing its angle of attack. So we really define it in terms of the flow direction.
But you see it's different sometimes, because some people that value with respect to the wing, and I think it's very confusing that it's not correct. Because what lift is, just look in the dictionary, it means something, right?
Yeah.
it means not falling.
Yeah,
Falling is because there is gravity.
I can also give you these graphs in the wing perspective, but that's not helpful at all. That's not going to make things clear.
Task for you.
Yeah.
I only wanted to know your convention.
Yeah, no, I understand. Yeah, so if we compare these results to the model of Professor Riemakers, you can also see that this peak, this thrust peak is around minus 60 degrees. The efficiency we still have to calculate, but for now this seems to, the thrust part seems to match pretty well. The power, we still need to split the inertial component and the aerodynamic component to say something about that. That's a challenge that we're still facing. Yeah, and that's what I could quickly put together for Riccardo's presentation. Any questions on that part?
Excellent.
I have an additional question. What about the moments?
The moments, we also have those. We're still analyzing. So we got this data a couple of weeks ago, so we're still in the process of analyzing it. Yeah.
Takes a moment.
It takes a moment, exactly. Yeah. Yeah. Okay. So if there are no other questions, then
Thank you very much. Riccardo.
yeah.